Today's lecture is usually a pretty popular one. It's about data structures, which many of you have been exposed at least a little bit before. I know the undergraduate class has data structures as a prerequisite. Um, but the point of emphasis today is we're going to try to get really, really simple data structures, maybe even simpler for the same ends, uh, as some of the tasks you might have seen in this previous class. But there will be a little bit more sophistication in the analysis because we're going to use something called amortized analysis. Okay, which is a little unfamiliar, so it might be awkward at first. But ultimately, the trade-off's great because you get these really simple data structures, which often leads to, kind of like really good performance in real life because that's sort of like the big O we always ignore is very small compared to other comparable solutions. Um, and, there's a little more burden on us to analyze it, but that's okay because you just have to analyze it once and the computer uses it forever. So usually we're okay with that. Okay, so let's start with, yeah. And this is going to be like one half of, so the next, I guess, 2 weeks or so was in solar eclipse in the middle. We're going to talk about average case analysis of algorithms, but in a very specific, precise sense of the word average. So we are not going to sacrifice like worst case inputs. I'm not saying we're solving random SAT formulas or sorting random permutations of numbers. So in data structures, we're going to have worst case inputs and we're going to kind of analyze their average performance in hindsight. I'll explain what that means. That's what today's about. And then we'll also talk about algorithms that take worst case inputs, but then do something random. They flip some coins to make some decisions. Okay. And we're not going to worry about cases where we get really unlucky with our coins so much. We're going to analyze their expected running time, their average running time in the probabilistic sense. Okay, so that's two notions of average running time. They're often very practical. They seem to correlate well with our perception of the performance of these algorithms, but we're not going to lose any of the robustness of can we handle all inputs. Okay, so you're still going to get very, very sound algorithms. Often, actually, these algorithms are very practical. They're very slick. Okay, but sometimes there's a little bit more. There's this extra layer of, okay, our thinking is a little different. Our analysis is a little different because we're relaxing a little bit, right? In the analysis, we're allowing for average case instead of worst case in some specific notion of average. But that degree of freedom, lets us do more algorithmically. Question? Oh, I will also give some examples of algorithms where interior steps are amortized later. But often you start with data structure. That's what usually people have in mind. Yeah. So, okay. All right, so here's something we've all seen before, right? You have an integer I and you want to increment, so you call I plus plus, right? So in terms of bits, starting from 0, 0, 1, add 1, 1 bit flips, you carry the 1, 1, 0, that's 3, that's 2 in binary, 1, 1, that's 3 in binary, 2 bits flip, carry the 1, now you have 4 in binary, 5, I hope. Okay. So our basic question is, how long does I plus plus take? Probably you've always thought of it being very fast, but how long does it actually take if we're being very precise? Is it log n? What is n? Okay, so I think, so is it, so like take this one, is it log of 3 or is it 3? Because that's log of 3. Okay, there's three numbers, 1, 0, 0. So you're saying it takes time 3, proportional to the number of bits, or are you saying it takes time log 3? Takes 3. Okay, okay. So the running time can be proportional to the number of bits, right? Because what's the worst case? Yeah. So it's quite possible that something like this happens. Uh, I think I was once very careful to make sure there's actually as many zeros on the second line as ones on the top, but I think I did something like copy and paste to kind of clone these. Uh, but if there's k ones in a row, you're gonna have to carry the one k times, right? You have to look at all the bits just to this increment. Now, you've all done I++ before, right? That would mean like if that was really like realistic, then it's like, oh, you do a for loop from I equals 1 to n or something, which has log n bits, and you're not paying like log square n time total, which is, or no, n log n, or no, let me do this. Okay, let me back up. So the real question, I think, is not on a single integer, what's the worst case number of bits, but say as you increase from 1 to n, how many total flips do you make? Right? Because if you're using this in a for loop or something, you're going from 1 to n, that's really the total time you're incurring. Right? You're probably not that interested in a single one because you're just using the integer somewhere in your algorithm. What you want to know is what's the total amount of time it's taking me to increment the integer over the course of my algorithm, which if I divide out by the number of times I increment, maybe it could also be a question of what's the average number of flips per increment. Okay. Right. So what is the total number of bits that get flipped as I goes from 1 to n? Okay, so let's do that. Let's look at the least significant bit, calling that the first bit. How often does it flip? Every time. From 0 to 1 or 1 to 0. So both count as a flip. I just mean the bit changes. Okay. Uh, so over n increments, how many times does it flip? N times. Okay. What about the second bit? Okay. Every 2 times, n over 2. What about the third bit? Every 4 times it flips, n over 4, right? So the kth bit, how often does it flip? Every 2 to the k minus 1 times, I guess, technically, if you're careful. So you're paying like n over 2 to the k minus 1, right? So what happens when we add the total number of flips is just going to be adding up this column over all k's. What do we get? Huh? So n plus n over 2 plus n over 4 plus n over 8. 2n, right? Or take the n out. 1 plus 1 half plus 1 fourth plus 1 eighth plus 1 16th. The geometrically decreasing sequence is just a constant. Okay, so um, that's it. So each increment takes a constant time on average. Okay, as I go from 1 to n. But in a very rigorous sense of the word average, no matter where I ended n, if I look back, it would have taken constant time on average. Okay, so it's not like the big flips are at the beginning or something, and then we decrease the average over time. At any point in time, your worst case average. Okay, so we call this constant amortized time, right? And this probably is much closer to what you actually think of the running time of I++. Yeah, so maybe your intuition was justified. Okay, um, so that's what amortized analysis is. So if I have a data structure with only one operation, I'll say it takes t amortized time. T could be a constant, t could be log n, t could be something else. If any n operations take big O of nt time. Okay, so when I divide out by the number of operations, it always looks like it took big O of t time at worst in hindsight. You can expand this out to multiple operations. So if I have like I don't know, a stack, you can push and you can pop. A queue, you can insert, you can remove. Search trees, you insert, delete, these kinds of things. So maybe you have different operations, and I can say, okay, the first operation takes T1 amortized time, second operation takes T2 amortized time, so that if I ever have some sequence of operations, the total time should correspond to adding up the corresponding T1, T2, T3. So if it was like operation 3 followed by operation 2, followed by operation 5, the total time should be at most T2 plus or T3 plus T2 plus T5, if I remember my made up sequence correctly. Okay, so that's amortized analysis. Okay, there's many ways to pull off an amortized analysis. So at the end of the day, you need to come up with T1, T2, and T3 and be able to justify that it does meet the definition. But over time, we've also come up with these sort of like heuristics or different ways of maybe thinking about it that helps some people come up with an amortized analysis. Okay. Um, and so they're just, tools to help us work through it. Okay, so that's what we'll cover. This credit scheme and something called a potential method. Okay. Oh, I should mention that when you have multiple operations, uh, T1, T2, T3, they may not even be unique. There may be different trade-offs where you make T1 bigger or T2 lower and it'll still be okay. So that's also something that can come up. That's okay. Okay, good. So let me use the binary counter to introduce these two other approaches, and then we'll start doing some new stuff. Or, well, stuff you've seen before, but at least something other than binary counters. So the idea behind credit schemes, um, yeah, so it's just like a credit account. Um, you can buy credits ahead of time to pay for work later. Right. So when we're trying to get like good average running time, what I'm kind of saying is like, oh, that really expensive operation later that would have killed my worst case running time. I want to kind of justify that I can divide it out to something small, over many operations. So the idea here is to sort of like try to anticipate that by sort of like saying, okay, I'm going to just put like 10 units of work in the bank that can be used later, 10 units of work in the bank that can be used later, things like this, so that when that big operation comes up, you've sort of already paid ahead of time for that big work you're going to do. I'll give an example and that'll help clarify, but that's the idea. And right, so the rules are you start with 0 credits and you must always have a non-negative amount of credit. You cannot be negative credit. So you can just buy IOUs for later or something like this, but you can't owe. And I don't know, I lost the analogy. But so the number of credits in the bank needs to be non-negative at any point in time. And so if you can come up with some kind of system where like, okay, for each operation, I'm going to buy this many credits and then I'm going to pay this many credits. You have some rules. I'll make that concrete. And if you can show that, okay, you always keep your balance non-negative, and you can show that for any operation, the running time plus your change in credit is some at most 10 or something, then your amortized time will be at most 10. You can add them up at the end. So I will demonstrate this by example with binary counter, and then the proof to actually generalize it to like arbitrary operations is very similar and in the notes. But I think it's more fun to get some practice using these things than to worry about that. So let's take our binary counter example. We already know it's constant amortized time by just directly analyzing it. Okay. But we're going to try to come up with an argument based on credit schemes. Okay, so each operation I want to buy a certain number of credits and be able to clearly explain that, whenever I have to flip a ton of bits, I have as many credits in the bank as needed to flip all those bits. So any ideas? Oh, okay. we know we probably should buy a constant amount of credit because we're going for a constant amortized bound. So let's say I buy like 2 credits or 3 credits, doesn't matter. But I want to argue that every time I flip k bits, I have k credits ready, right? So sometimes it's not just a matter of determining how many credits you buy, but finding a nice way to sort of organize them. Like, you can imagine putting them in different accounts, where an account is for a particular operation later, if that makes sense. Maybe it doesn't. So let me just walk through it. So let's say you buy 2 credits for every increment. Okay. What we're going to do is we're going to put 1 credit on the first bit. Okay. And credits are infinitely divisible because it's just a math made up thing. So I'm going to put half a credit on the second bit. Okay. A fourth of a credit on the third bit. And I'll keep going like this. I'll put 1 over 2 to the I minus 1 credits on the ith bit. Okay. You add that all up, I'm only distributing and buying 2 extra credits in each operation. So let's say I call I++, I'll immediately buy 2 total credits and spread them out like this. Now I need to flip the bits. But, the first bit is going to be flipped, but I always have a credit in the bank. The second bit flips every 2 times, at which point we'll have 1 credit from 2 of these half credits. The third bit only flips once every 4th time, but whenever that comes up, I already have 4 credits in the bank. Okay? So, by sort of organizing or conceptualizing the 2 credits we buy this way, kind of like different accounts for each bit, I can guarantee that every time I need to flip bit I have 1 full credit reserved for flipping that bit. And I'll always be able to pay for flipping, yeah. So maybe this is too simple of an example. So this is just trying to introduce what this credit scheme is. I think when we do more complicated ones, yeah, maybe it also depends on your personality, which technique you prefer. So it's possible this is not sophisticated enough to really excite you. Yeah. Okay, so that's an example of credit schemes. Um, uh, yeah, so that's the basic idea. The main rule is you can only spend credits that you've already saved. You can't go negative on credit. All right. Good. Okay, so and you can see in the notes that for any kind of generic situation, if you just can set up some kind of credit strategy and guarantee you never go negative, you can always get this amortized bound. All right. All right. The next method is, I guess, inspired by physics. Where you have potential energy and things like that. If you're high in the air, when you fall, like you'll go faster. Okay. So the idea is to take the state of your data structure, okay, and assign some kind of potential to it. Okay. And, well, I mean, if you just think about what I guess potential energy does in physics, right? It sort of accounts for the energy loss when you're going up a mountain. Okay, the potential energy goes up, you'll recover it when you go down, something like this, right? So, what you kind of want to argue is that uh, when I have to pay for a really expensive operation later, the potential will go down by enough to pay for it. Okay, you can also think of it kind of like a bank account. But anyway, so you have some kind of potential, and that's not right. Okay. Uh, and the idea is that for each operation, you're going to pay for increases in the potential, and then you get paid back for decrease in potential in the running time. So the potential decreases by 10, you get 10 free units of running time. And so you keep going like this kind of thing. And yeah, so this is going to be what's called a potential argument. So right. So the potential needs to always should be non-negative. So maybe this is a little bit misleading because it looks like you actually went down from where you start. So it should really not be the case, but I didn't want to redraw the picture. Um, So sort of like how we had changing credit, um, if you can come up with a potential scheme to describe it, okay, and you can bound real time plus change in potential, that will translate to an amortized bound. Okay, just like how real time plus change in credit also gave you an amortized bound. Okay. So, and if you want, you can see a credit scheme as a potential method where the potential is how many credits you have in a bank. But yeah, that doesn't matter too much. It's just a matter of, finding a appropriate metaphor to help you pull off a good analysis. Okay, so let's take a binary counter. I want to come up with a potential function uh, for a binary counter uh, that fully explains away why I shouldn't worry about the big operations when I have to flip lots of bits. So you're looking for like some kind of sentence description. Oh, given a binary counter, I just get this number. Yeah. Oh, okay. You get 25%. Good. Anyone else? It's getting bleak. Okay. Um, okay. So here's what we'll do. We're going to set phi to be the number of bits set to 1 at a particular point in time in the counter. So initially the potential is 0 because all the bits are 0, right? And now every time, so no matter wherever you increment, only one bit is going to go from 0 to 1. That's going to be the last bit that gets flipped, right? So, and meanwhile, so the potential is always going to go up by 1 for that one bit. But every time you reset a bit from 1 back to 0, the potential goes down by 1, and that will pay for the work to go from 1 to 0. So all the flipping back down gets paid for free. So that's right. So you only ever set one bit to 1 in any increment. So you're going to pay 1, and then all your other flips are setting 1s to 0s, and those are paid for by your potential. Every time you set 1 to 0, the potential releases 1 unit of work, okay, because the number of 1s has gone down, and that pays for the running time. Okay. So sometimes potential functions, I mean, this feels a little bit clever, maybe, right? Just like, oh, because it kind of captures the essence in one slick sentence. So sometimes potential function is not the most popular method because it can seem hard to come up with a good description. On the other hand, it's like sometimes the easiest to verify everything at the end. Yeah, if you get the right sentence, then you could easily see why uh, the operations are paid for. All right, so those are the three methods by example of counters. Just a direct analysis, appealing directly to the definition. Credit schemes, where you kind of think of, oh, I pay for work for later, and the potential function method, okay, where you find some way to sort of take your data structure and just kind of capture the pent up work ahead of you with an appropriate sentence description. Okay, good. So now comes maybe a more fun part because we get to actually make things. Okay, so I assume everyone uses Python, so you just use lists all day. Does anyone use Java? Okay. Does anyone know how array lists are implemented in Java? So no, it's not. It's not implemented by a linked list. That's why it's called array list. Yeah. Okay. So if you want to back a list with an array, right? Here's the basic. Arrays are great. You can access anything in constant time. The obvious problem is if you allocate n slots, and here comes n plus 1, you're screwed. To make a new array of size n plus 1, that would be spending like O(n) time every time you do an insertion. That's terrible. Okay. So yeah, so what's the trick for those who don't know? I guess if I only ask the people who don't know, they don't answer. Okay. Okay, so we're going to do what's called this doubling trick, right? Whenever you run out of room in your array, you've used up all n slots, here comes n plus 1. Don't allocate an array of size just one more, right? Make it twice as big. Okay? Spend n time copying it, and then put in the new one. Okay, so every once in a while, you're going to have a big and expensive operation. All right, so that's maybe our first challenge, new challenge. The claim is that if you do this doubling trick, well, first you can do lookup in constant time because it's always in an array. So that's great. And you can append in constant amortized time. Clearly, it's not constant worst case time because you occasionally have to allocate a massive array. But we're going to argue it's constant amortized time. Okay. So, yeah. And I think on the homework, we'll ask you to make a suitable implementation adjustment so that you can also delete from the end in constant time. The obvious risk here is that, if you keep inserting, deleting, naively, it could be bad, right? You always. So, but I think by the end of this, you'll see how to do this. Okay, so we can pick any method you want. I left a space blank. How can we argue that appends take constant amortized time? Yeah. Yeah, so that's sort of the definition. Yeah. But how do we actually pull it off? Yeah. Okay, so this would maybe be a more direct analysis then. So after n, or maybe over n insertions, I guess for every, it's only when you double, right? So maybe for I is equal to 1, 2, up to log n, uh, uh, the 2 to the ith append takes big O of 2 to the I time. Otherwise, it takes constant time, which is not a big deal. So we can kind of ignore it, right? Yeah. Yeah, so now we just need to sum this up, right? What is this sum? Yeah, 1 plus 2 plus 4 plus 8 plus 16 plus 32. It's always going to be within a factor 2 of the largest. Are you concerned about the log n versus log n minus 1? I'm going to piss you off more. I'll put a 5 there. It doesn't matter. Okay, so only when you go up by a power of 2 until roughly log n, you always pay 2. So 1 plus 2 plus 4 plus 8 is going to be 15. Plus 16 will be 31, right? Another way to see this is You can divide by 1 over n, 2 to the I minus log n, which is going to be going like 1 plus 1 half plus 1 fourth plus 1 eighth if you go the opposite direction down the sum. And that sums up to 1 or 2. Yeah. Okay, so this all adds up to n total time over n insertions. So you just divide, right? So if you paid constant time for each one, it'll be okay. Okay. Maybe for educational purposes, so that would work. Does anyone want to volunteer either a credit scheme or a potential function proof? Yeah. Yeah, so maybe every time, unfortunately that's not a power of 2 in the example, but every time so let's say I doubled at this point previously, every time I add a new element, I'll pay say 2 credits. Doesn't really matter, it could be a constant number of credits, right? So I will put real effort into this. There's a coin here and a coin here and a coin here, right? And now when I'm ready to double, right? So I just went from like 16 to 32, and now I'm going to go from 32 to 64. The last 16, since my last doubling, all have a couple coins on it. And so I'll have, say, 32 coins, and that will pay for making a new array and copying the whole 32 over. So one thing important is that these new ones are paying for the old ones. So I just doubled the extra coins to make sure I have enough. But doubling is not a big deal, it's still a constant. Okay. All right, so that's one credit scheme then. That would work. Okay. And then finally, what about potential method?
or
25%. Yeah. So how do you describe the, so I'm looking for like a sentence where I can just look at the data structure and infer the potential, not worry about the exact order of operations to get to this point. Ah, okay. Number of empty slots in the array. Okay. So now every time I fill this up, the potential is, oh wait, is that, no, that's not what we want. We want, I guess n minus the number of empty slots. Uh, so, so total size, minus number of empty slots, or something like this. Uh, so this goes all the way down, goes all the way up to n. And then, oh, maybe this doesn't quite work. Uh, yeah. Uh, yeah. High potential means that we got big work upcoming. Uh, well, okay, so I want to argue that when I go to a bigger array, the potential's gone down, right? So what can we do? Maybe potential function is not good for this one. I thought I have one in the notes, but I forget. Uh, yeah, anyone have an idea? Fraction of slots filled. Okay. Fraction of slots filled means what? But that's always between 0 and 1. So I want to argue that when I double things, uh, hmm. So ideally we want the potential to be very high when this is filled, and it's going to go back down when we double, so that it can pay for the work. Yeah, we can do that. Uh, just make sure. Okay, let's do that. Minus the size over 2. Um, good. So here, imagine I had drawn 8 instead of 7. Okay. Um, so here you're going to have uh, 8 occupied minus 4 is the size over 2. So you have potential 4. And then you're going to go down here, we're going to go to 16, and 8 will be occupied. And so you get 8 minus, yeah. Oh, so I can count 1 unit of potential to count as 2 units of work. Yeah, that's okay. Doesn't have to be 1 for 1, just has to be. In fact, you could choose even one factor, like you can do a log n factor or something if you wanted, like 1 unit of potential is worth log n units of work. But you just have to remember that when you state the overall running time, like you need to take that into account. It's easiest maybe to just think of it as a 1. Yeah. Equivalently, I can always put a constant around this, right? And that'll be okay. Okay, good. So I think this works. Number of occupied minus size divided by 4, something like this. Size divided by 2. Maybe size over 4 still works actually. But anyway, it doesn't matter. Okay, good. So I think this one, not a great case for a potential function. Okay, good, good. All right, here's a fun one that you've all seen before. So search trees, right? So in a binary search tree, the idea is to arrange you have all your data, all your keys are say integers. It could be anything comparable, like strings in alphabetical order, things like this. And you're going to store them in a tree so that if I look at the root, smaller numbers will be on the left, bigger numbers will be on the right, and it'll be that way all the way down. Right? So I guess many of you have seen search trees before, and maybe you've done these like really complicated red-black trees or something. Has anyone here been exposed to the horrors of red-black trees? Yeah, and other things. Okay, yeah. All right. So, but having the keys in this order are very, very convenient because you can do basic operations. Like, not only can you ask if a key is in your tree, but you can ask like, what's the first key that comes after? Because it's already in order, so you just have to. We'll step through it. You can list keys in between. So, okay. So if I ask something like, does this tree contain the number 7? As you all know, you start at the root, 10. Okay, it's smaller. That takes me to 5. It's bigger. Takes me to 8. Smaller, 6. Okay, it should be here. It's not here. 7's not in the tree. Okay, if I want to list all vertices between 7 and 16, okay, then what you can do is first kind of figure out where 7 and 18 or 7 and 18 are supposed to be. right? 7's not here. And similarly, 18 would be over here, over here, over here, over here, right? But it's not there. And so you sort of have like, carved this path around 7 and 18. And now you can just walk back through it. And sort of like all of the things on the right side or on the inside in a way. You say, oh, okay, 8's in between 10, 12, 15, 17, right? Just kind of knowing where you are and which side 18 is, tells you whether or not to include 21, things like this. Okay, so you can just carve it out and then you can just list them off. Another thing like how many keys are between 5 and 25? Okay. Of course, we can list off all the keys like before and just count them. But you could do something a little bit more clever. How can you support this operation to be faster? So I'm going to do DFS. Oh, so that means you want to like build out a whole list? Ah, okay. But the only issue is that now if you start inserting things in the middle, then you have to start over. So yeah, okay. Yeah. So it's going to include like this whole subtree here, right? Here 8, 6, 9. And it's also going to include like this whole subtree 17, 9, and 12 and things like this, right? And you sort of know like, oh, it has everything in the subtree. I don't need to really visit everyone. So if I write down how many nodes are in each subtree, right? Okay, this has 3, 1, 2, 3, 4, 5. This has 5. This has 3. This has 2. Up above, 1, 2, 3, something like this, right? Um, if you write down a number of nodes in each subtree, then you can just like kind of skip all of these interior subtrees that aren't so interesting and just add up the number quickly. So that's another technique. So all these operations take time, really, in the worst case, proportional to the height of your tree, because you have to figure out like where those endpoints are going to be. Even if you're doing these aggregation tricks, you still need to, get to the bottom. So, like, what would be a really good tree? Yeah, something that's like totally balanced. What would be a really bad tree? Something like this, right? And okay. Now, when you're maintaining a binary search tree, clearly the easiest way to like insert something is like, oh, let me go find where it should be and just put it there as a leaf, right? So that seems like, okay, I can code this. This seems like the obvious thing to do. But, you know, oh, yeah, so if I wanted to create a really bad tree, how would I insert these keys 1 through 7? An increasing order, right? Which is like probably the most common insertion order you'll see probably in practice, right? So this very natural idea of just inserting all the way down uh, can easily lead to unbalanced trees, and then you're suddenly paying linear time to do all your operations. Okay, so good. Um, okay, I have enough time to at least explain the data structure, and then we can analyze it next time. Okay, so at least you get a little bit of a punchline. So there's all these data structures that are obsessed with, okay, how do I keep the tree balanced, right? So I don't really remember what AVL trees do, and I don't really remember the red-black trees either. I just remember you like mark some nodes red, some nodes black, and if you have like weird color patterns, then you start doing mysterious things, right? Okay. Yeah, maybe some of you remember. For me, it's been a long time. So I'm going to suggest something that's incredibly lazy. Okay. Okay. So We're going to do something like before. I'm going to write down the number of nodes in every subtree. So I'll keep track of the counts. Now, okay, and I'm just going to insert things like normal. Okay, so I'm not changing the algorithm at all, but I am maintaining the counts. Now, I want the tree to be pretty balanced, right? So suppose I find out that there's one subtree that's like twice as big as the other. What should I do? Hmm? Move nodes around. Well, yeah, we're going to rebuild the entire tree. This is already in sorted order, so it's very easy to find like, oh, what's the median in this list? That'll be my new root, and I'll just make a perfect tree of 151 nodes in this case. Okay, so I want a balanced tree. Whenever something gets really unbalanced, I'll just rebuild it, right? Just list the things in an array and just chop it up, and it's very easy, right? Okay, so no big deal. Um, so what we'll show next time then is that by maintaining, balance just at each subtree, the height is always log n. So then all those operations you like to do will take log n time. The only issue, of course, is, obviously I'm rebuilding sometimes. That could take a while. So we're going to argue with amortization that this takes only log n amortized time, right? So then you get that log n time like we expect from our wonderful search trees, okay? But I think this algorithm is much simpler, much easier to remember, right? Just lazy rebuilding. Okay, so that's what we'll do next time. All right, thank you. All right, off we go. Let me remind us. Let me remind us where we left off Friday. So again, the theme, for this last sort of the last real theme we'll have in this class is two specific senses of the word of average case analysis of algorithms. Today we're focused on this amortized thing, which often is applied to data structures, but it is still worst case against any input, but it's always going to be averaging in hindsight. So we'll look at data structures that do many operations, and then look at the average running time and show it's always at most this in hindsight. So you still really get the full robustness, the full resilience of a worst case running time, but being able to kind of it gets, this is relaxed compared to a worst case every operation kind of running time, and that degree of freedom lets you do a lot of nice stuff. And then I think we'll have little time to at least get this started today. It's randomized algorithms, which again has worst case inputs. You don't control the input, but your algorithm will deliberately flip coins. Okay, so your algorithm will deliberately inject randomization into it, and then you're going to average over kind of the random outcomes. As if you had run your algorithm repeatedly, infinitely many times, what would the average come out to be, right? And that will also touch upon. I think that in both cases, you're going to get algorithms that are like really slick, really nice, really perform well in practice, because these are both a little more relaxed than pure worst case bounds, which means you have more algorithmic freedom, right? You have a little bit of wiggle room. The emphasis then will probably shift a little towards the analytical side, because we have to, it's a little bit less straightforward to argue that something has average case running time in either sense of the word, but hopefully with some practice we'll get used to some basic cases. Okay, so the first example we did last time was binary counter. The simple insight is, okay, you have a geometrically decreasing sequence. The 10th bit only gets flipped 2 to the 10th, 1 over 2 to the 10th time. So this is okay, even though you might flip a lot of bits in a single increment. The second one we looked at, well, okay, maybe I should mention that there's a few different ways to analyze amortized analysis. One is a direct analysis, appealing directly to this definition, which is something like Okay, this operation has t amortized time. If I run it, 100 times, it should take 100 times t total time. Okay. Um, but then there's other ways to do it, like credit schemes, where sort of like each operation you pay a little extra, which you can trade in for work later, right? So in this sort of like in hindsight counting, you're really trying to pay for it up front, and that makes it easier to justify. Things are good in hindsight. Another option is the potential function method. For the case of binary counters, you can just set phi to be a number of bits, set to 1, and then you'll see that just like pays off for everything. So I'll have a couple more examples this class to try one of these approaches. I think another thing we looked at last class was array back lists. And the basic thing is arrays are great because you can access them in constant time. The only issue is that when you're appending, if you run out of room, what are you going to do? Like make a whole new array? And of course that's very clumsy, but if you just do this trick where you double each time, so as soon as I run out of room, I just make an array twice as big and fill up the next slot and copy everything over. There's many different ways to argue that, oh, this is not so bad on average. And I think that's what we showed. We showed that it'll get constant amortized time, even though it might look really bad for a single operation. Always in hindsight, in average, you're going to be okay. Because that way for you. Good. So we did that. And then we started this discussion about search trees. Right, so binary search trees where I have the keys in place. So that if I want to find a key, I just go left, right, things like this. We talked about some of the use cases of binary search, like not just finding a key, but listing all keys in a range or counting the number of keys in a range, things like this. These can be done fast in a tree, but the operations always take time proportional to the height of the tree. So, right. So a really good tree is one that's completely balanced, because then I can get to the bottom really fast in the worst case. And then the worst kind of tree is completely unbalanced, where it's basically a linked list and you're just walking all the way through looking for your key. Okay, so if you have a balanced tree, you're going to get these binary search kinds of running times. Okay, so, right. So there's a lot of effort put into how to keep a binary search tree balanced while keeping the keys in order, including these things that you may have seen before, like AVL trees or red-black trees, okay, which are like these very intricate schemes. In fact, I kind of forgot the details myself. And but today we're going to talk about a much lazier approach to balanced trees, and I think simpler. So just to recap, the first step is to write down for every subtree how many nodes are in the subtree. Right, so as you insert a key and it goes down to the bottom, you'll just update the count. Okay, well, plus one, it's not a big deal. And remember, our goal is to have balanced subtrees, so that will basically be our algorithm. Whenever I find a subtree where one side is, say, twice as big as the other, I'll just rebuild the whole thing. Okay, so here I have one subtree with 100, another subtree with 50. One is much heavier than the other. Only then I'll rebuild the entire tree. Okay, and you're keeping track of the count, so that's easy to notice. Okay, so the algorithm is like really, really simple. You have a decent chance of programming this thing without introducing bugs, right? So, but it would be nice if we can argue that it's a good algorithm. Okay, so here are our two lemmas, or two things we're going to prove. One is that the height is always about log n. Okay, and as long as the height is log n, then your lookup operations, like looking for a key, things like this, will take time proportional to log n. So that's great. Okay, now the only thing, so all the read kind of operations are okay. Now when you insert a key, okay, the height's not the only issue. It's true that you can find out where the key should go initially in log n time, but then inserting that key may tip the scales a little bit too much. right? And you have to rebuild some stuff. So that's doesn't you don't get log n for free, but we'll argue that it'll take log n amortized time, which is what you're hoping for. Okay, so that's the goal. Okay, so good. Let's do the first lemma, which will help motivate why we're doing this kind of local balancing. So the claim is as long as I'm local balancing, so that means that as long as I'm applying this algorithm, each subtree will be in a factor of 2 of the other. The height will always be at most log n times a constant. So why? So it's locally balanced. So what we want to argue at some level is that if your data structure is locally balanced, then it's sort of globally balanced, like the height will be log n. So I just want to argue that if each subtree within a factor of 2 all throughout the tree, then the overall tree will have height log n. Right? If it was exact parity, then that we've done many times. We know that it's always okay. So this is always, only up to a factor of 2, but do we still get the same conclusion? Yeah. Okay, so in the worst case, let's say I have n total vertices, right? In the worst case, like the most lopsided thing. So maybe it's something like this, right? So over here, you'll have n over 3 vertices, and you have 2n over 3 vertices, right? And this will go into two subtrees, and the bigger one will be down to like 4n over 9, something, right? 2n over 2/3 of 2/3. So each time you're going down, the maximum subtree has 2/3 squared times n, 2/3 cubed times n, right? So how many times would you need to go down before you get down to 1? Yeah, log 3/2 actually of n. And yeah, that constant never actually matters. Okay? As long as you have some constant that's like strictly bigger than 1, this here should be maybe like log base 3/2 of 2 or something, I don't know. Okay? So good. Okay. Another way, or a lazy way to see this is if you take 2/3 squared, that's 4/9, that's less than half. So every 2 levels, you're halving the number of vertices. Okay, so good. All right, so height's always log n. So that at least justifies why I want to keep things locally balanced. So now let's try to argue that insertion takes log n time. So let me maybe make the algorithm clear. So you're going to take your key and you're going to search for the right place to insert it. And maybe it's like here. So all these counts go up by 1. And then you're going to go up the tree and you're going to compare, your size to all the adjacent sides and see if you've tipped the scales enough to rebuild. So you rebuild from bottom up. Yeah. I guess you could also just find the top one. It doesn't matter too much. You could find the biggest one where you upset the scales and that'll fix everything down below anyway. So yeah, it doesn't matter. Okay. So you're going to insert, update the counts, then look at the counts, see if you have some rebuilding to do. Okay. So since the height is log n, it'll take you log n time to get to the bottom, and you update log n counters on the way up. Okay. Now the question is, occasionally you're going to do these massive rebuilds. How do I pay for the rebuild? Well, okay, so keep in mind that you may rebuild like n over 2 vertices. You might even rebuild from the root. So the total amount of work could be massive. Yeah. Yeah, so we can do like so we will do like a potential function. But what I'll do is I'll define a potential function for each node in the tree, and then the total potential will add everything up. So uh so if this was some vertex, some node x, I might write phi of x is equal to uh maybe the number of vertices in the left subtree. I'm just kind of making up some notation. Minus the number of vertices in the right subtree, the absolute difference. Okay, and I'll have that for every node. Okay, so right, so this is sort of the unbalance, right? The difference between the two. So first, when I go down and I update all these counters, so all of these potential, individual potentials change, right? But they're only changing by one for each one, and there's only log n of them. So when I go down, I'm only going to increase the potential initially by log n. Now, when I find myself fixing, when I find myself fixing an unbalanced tree, right? So this will have like k vertices, and this will have at least 2k vertices, okay, for some k. And our potential for this node will be equal to, or it will be at least k, right? Because one is twice as big as the other. And I'm going to go through and rebuild the whole thing, right? So what does that mean? We start there, and this is going to become, right, kind of running out of room. So this will become perfectly balanced, right? This will be like 3k over 2, 3k over 2, and your new potential, all right, phi prime of x, is going to be like at most 1 or something. There might be like, off by 1 kind of imbalance. So no big deal. Okay, so as I go from here to here, my potential will go down by k. Why is that good? Yeah, this will take me like 3k time to rebuild this tree. It's already in order, so I just have to lay it out in an array, and then I just pick out the middle and do the two halves, and it's not so hard to rebuild a tree that's already sorted and make it balanced, right? So this will take me linear time in k, and I'm getting k units of potential back, so that will pay for the rebuild. Okay, so unit potential I'll think of as, I don't know, 10 units of a computer time or 100 units, enough to make up for that constant factor. So that's it. So by just having measuring the disparity at each subtree, you can justify rebuilding in hindsight. Okay, pretty simple. Questions? Okay, it's like a funny analysis, but I think the algorithm is very appealing. Okay, so good. So that's insertions. Now, what about deletions? How do we delete? Anyone remember how to delete a node from a binary search tree? Yeah. So the first step is like you find a key, right? It's somewhere in the tree, right? And if you're lucky, it'll be a leaf. If it's a leaf, you can just delete it, right? All right. So now the tricky part is, okay, what do you do if the key is not a leaf? It's somewhere in the middle, right? And then, yeah, one option is like to try to find a successor or something. But even this is like a little bit complicated. So like, if it kind of looked like this and the successor is here, and if you remove that, then you have to keep going down to replace the successor, things like this, right? So, you can do it, but it's like very complicated. It's very messy, right? At least that's my memory of it. Because you have to fill the hole, you find the next key to fill the hole, but that makes a new hole, you have to fill that hole, and you just like, this never ends, right? So, okay. So, what's an easier way to manage deletions? Yeah. Yeah. So this is what we're going to do instead. If you're going to delete a node, I'll just mark it as deleted. Just set a Boolean flag. From now on, when I search for it, I'll go right by. I'll continue to use the key to decide left or right, but I won't return it if I'm looking for that key. Okay. And then if at least half the nodes in the tree are marked for deletion, then I'll rebuild the whole thing. So if you have n nodes in your tree, at least n over 2 are real keys. Yeah. Okay, so that's a good question. So I think that gets into our next point. Okay, so the claim is that uh, even if I instrument, now I add lazy deletions to my data structure. So now we have lazy insertions and deletions. We can still argue they both take log n amortized time. And this will be a little more interesting maybe because we're mixing two operations for the first time. Okay. So now to get to your point, how do I try to justify this? So maybe one thing I should point out is that we need to it won't be too hard for us, but we need to redo the lazy insertion part because it's a different algorithm now. Okay, and then we also need to account for the deletions. So how could we, remember earlier our idea for lazy insertions was disparity between the number of nodes in each subtree. But now number of nodes is slightly ambiguous because we have some marked for deletion and not, right? So what would be a good potential function just modifying or clarifying how to interpret our previous construction or proof with deletions? Okay, so that idea is number of, I guess, x dot left dot not deleted. I feel like I'm setting a very bad example. This is not, you should be better than this on your homework. Okay. But, okay, so one option is to count the disparity of the nodes that are not deleted and how unbalanced they are. Okay. Um, okay. And the other option is to count any nodes, deleted or not, right? So alternatively, you can do number of nodes in the left subtree minus the number of nodes in the right subtree. Okay. I'm trying to think of a good explanation why, but I was planning to take the latter approach. Although it's not impossible to maybe get the first one to work. But let's try the latter. Yeah, sorry? Of total nodes, marked or not. Yeah. Yeah, when you rebalance, you can just or you can delete the marked nodes on the spot. Um, yeah, yeah. I think one of my worries here is that um, uh, one of my worries here is that if I'm actually searching for a key, you might be going into subtrees with tons of deleted nodes. Okay, and um, and you might get very high height. Is that? I mean, at least if it's just like this. So my worry is that both sides have the same number of not deleted nodes, um, but this side has just tons and tons of like deleted nodes, and right. Okay. So maybe something like this is doable, but maybe you'd have to also keep a counter of. Okay, yeah. So maybe here's one issue I'm a little bit worried about. So maybe you like get into this massive tree where everything is deleted, and then you just have one good leaf that you're looking for, and you're going to pay time that's like logarithmic in a number of um, yeah. Well, I actually think this can be eventually justified, but I think it'll be a little bit messier than what I had in mind. Because one will we need to address the fact that okay, I can have this massive tree. Yeah, you can have a massive tree where everything here is deleted except for one thing that's not deleted, and this doesn't even have to be balanced because there's no balance required among your not among your deleted vertices. This would count deleted and not deleted. So just the total nodes out there, and it'll always be balanced. So it'll be easier just to say, oh, it's logarithmic in the total number of nodes in the tree. So at least I find that a little easier than the first one. But I think this one could eventually be made done. Yeah. Yeah, yeah. So some level, like, yeah, you're worried about so if you did the first rule, then the way you're shaping your tree is not taking into account the deleted nodes. So what you're basically worried about is cases where, all the deleted nodes are like, say, making long paths in your tree, but you don't really care because it's not directly being taken into account in your potential function that's doing the rebalancing. But if we just do x dot left, x dot right, I mean, we're really navigating all the nodes, deleted or not. So this at least matches that intuition a little bit more closely. One could maybe like try to bring into conjunction that later feature. We're going to try to delete half the, make sure at most half the nodes are bad or something. But anyway, yeah. So, okay, so I'm going to go with the second definition, like what we had before. So this is any node marked or not. Okay, and just like before, um, the height will always be logarithmic in the total number of tree nodes in your tree, which if we just maintain this deletion rule, will always be within a factor of 2 of the actual number of nodes. So you'll still stay log n, where n is the true number of keys in your tree. Okay, so that's okay. So you can rebalance this way. That otherwise, the same rebalancing argument works. If I have really lopsided thing, I can fix everything. I can also, in that pass, if I wanted, remove the deleted keys. That won't create any work for us. Okay, so, but now I do need to account for, in my entire tree, at least half the keys became bad. You can sort of think of this as garbage collection. You can also argue garbage collection is amortized, right? Because You just kind of do your thing until you realize, okay, half the keys out there are junk. I need to clean them up. So what would be a potential function to justify deletion? So, so you can always make many potential functions, right? One for different purposes. Here we even made a different potential function for each subtree, and then we just added everything up. So likewise here, I think for deletion, let's just make a new potential function to do deletion, and then you get an overall potential by just throwing everything together, adding them all up. So the direct answer is we can do a separate one, but the actual answer is no difference because we add them all up together at the end. Yeah. Yeah. Huh? Okay. Here's a potential function. The number of marked vertices minus the number of unmarked vertices. Okay. So let's say I trigger a. Sure, you can do absolute value. Okay. So when we do a cleanup, what would the potential function be? Potential value, the value of this potential function be? It would be the number of nodes marked for deletion minus the number of nodes that aren't marked for deletion. And we did this as soon as half of them became marked for deletion. So it'll be actually 0. And then we'll clean everything up, and it'll go up. So this is like the opposite of a good potential function. So we want something where the potential is very high when there's the work to be done, and the potential goes down when we do the work. Yeah. So we just did the number of marked nodes. If there's 100 marked nodes but 200 total nodes total, I get 100 units of potential. That pays for my 200 units of work. So that's it. So the two things, one is we kind of do the same disparity potential as before, except it's including the nodes marked for deletion. Okay. And then we have a second potential that's just counting the number of nodes that are marked for deletion. And then you put that together, that's one big potential function. Okay, so that's it. Not so bad. I think it's a weird kind of analysis, but otherwise, in hindsight, it's sometimes kind of clean. And certainly the algorithms are very nice. Any questions? You want the potential function to pay for your extra work. So I can think of 1 unit potential as big O1 work. Yeah, yeah. So I should also mention that when you delete a node, you go down log n levels, that takes log n time, plus this potential goes up by 1. So you pay an extra 1, but of course that's not a big deal. Okay, so, okay. All right, great. So that is that. What's next? Okay. Does anyone recognize like these languages? Has anyone messed with Haskell before? Really? Haskell's great. Hopefully it's not pronounced Haskell. I think it's pronounced Haskell. How about Clojure? How about Lisp? The hell? Come on, guys. This is computer science. Okay, Haskell's an amazing language. I really liked, you could knock out like a Saturday doing this, learn new Haskell for great good. It's very nice. So it's a purely functional language by someone who really took the wording purely functional very seriously to an extreme, and it comes out very elegant. But so in purely functional languages, you kind of want to think about things like stateless and, a little bit more like a mathematician would think about it. So as a general rule, when something is written down, right, you make some changes, you make some data, you will never change that data ever again. Okay, that's sort of the rule behind immutability. So when you write something down, you'll just never change it. Okay, no writing in place. Okay, now that seems strict and severe, but actually it brings a lot of benefits. So this whole like never rewrite, never change policy, it means you have no side effects, right? I have some piece of data, I give it to some other piece of code, and that code can do whatever it wants with it, but it can't change it, right? So I can keep working with it. And which also does things like simplify concurrency, right? Because you're worried about concurrent access to the same object, things getting changed, people having these inconsistent views, right? So I don't know, things like swap, I forget the exact name. But these like atomic swap operations are now a really great way to manage concurrency and things like this. So yeah, so I mean like this no side effects thing. I feel like if you're in a language like most languages, like Java or something, with side effects, over time you just end up falling into this pattern where whenever you give your object to some other part of the code, you do dot copy first so that it doesn't mess with your thing, right? So you end up converging to this anyway, except now you have dot copy all over your code. You just cannot be working in a big code base without this. So same with any concurrent situation, just do dot copy, dot copy, dot copy. Please don't break what I have, right? This can also help the compiler, right? So kind of this extra information, this will never change. Things like this is a very strong assumption, so the compiler can be more aggressive about certain optimizations. Oh, I can do this, do that, and I know nothing else will mess with it. Okay, so so an example, going back to the old Lisp days, is just like a linked list, right? So in Lisp, a linked list is called a concel, or a node is called a concel. So you have a car that points to some piece of data, your number, your name, whatever the data is down here, and then a pointer to the next concel that's called the Kadur. Okay. And if I want to add something to the linked list to the front, I just make a new concel that points to the top of the previous one with a new piece of data. Right? I don't have to change the existing list. I just prepend to the front, and now my algorithm is looking at the first concel and holding a pointer to that. Okay, so I can keep prepending to the linked list without changing any existing stuff. And I sort of have a new linked list, but I have not violated this rule of once something is written, it never changes. Okay? And then, if you've programmed in Lisp or anything, like a linked list is enough to do anything. Okay. So at some level, that's part of the ethos of Lisp. Like, okay, you can do linked lists. Can you do anything? Like, I don't know. Have you guys read this original paper by McCarthy? I mean, he set out to like say, oh, I can make a whole programming language out of like 12 commands. 3 of which are cons, car, and Kadur. And not only that, but this program language will be strong enough to write itself, right? So you're going to represent the whole program in a linked list. So now you have macros that are very easy because, you get these programs writing programs. Okay, so that's an amazing paper. Paul Graham has a nice essay about it as well. Okay, so another example, right? So, okay, you might be thinking like, okay, this is when you edit an object, right? So I have an object here with 2 fields, and I want to change B to something else. You'll have to copy and make a new copy of the object with that field changed, right? Which seems like, okay, not a big deal if the objects are small, but if the objects are big, that sucks because you have to copy a big object just to make a small change. Doesn't seem like a good idea. So, but often in these object-oriented systems, that's not how things are quite organized. Even a big object, they're usually not just based on having like a ton of fields, right? Usually it's because you have a couple fields, but then you have a pointer to other objects that point to other objects that point to other objects, right? This has the effect of a large complicated object, but this itself only has, in this picture, 5 pieces of data, two numbers, 3 pointers. So when I make this new object and I copy everything, and I need to quote unquote copy everything over, I don't have to copy all of the pointed to objects, right? So we just add new pointers to the existing objects, right? And then otherwise reuse the exact copies of the existing objects. So that gets you around some of these objections about, dealing with big objects. So a shallow copy is fine, basically. Okay, so, all right, so if this is so useful, you should be able to do some basic things. So what about stacks and queues? Okay, so as you know, here's like a stack. You put plates on top of the stack and you take plates off of the stack. Okay, and here's a queue. You're waiting in line to buy a movie ticket. You enter the back, you come out the front. Okay, basic processing stuff. Okay, so we need to implement these immutably. Data structures 101. So, how would you implement a stack? Immutably. Yeah. Yeah, so a stack is just a linked list. Okay? If I always have a pointer to the head. If I want to add an item on top, I make a new kind of block, point to the previous top of the stack, and now I have a pointer to the new top of the new stack. Okay? And I can do this, and someone else can have their own copy of the stack, and I'm not changing it because nothing is getting rewritten. Okay, so that's great. Now, how about queues? 2 pointers. So, okay, so here you're saying something like this. So you want to have a pointer here and a pointer there. Okay. So let's say that you want to remove from the bottom. Okay, so in our data structure, we would have to walk all the way down, find the second to last one, adjust our pointer to here, and release this. Okay, so that means in your data structure, there's always often like a dangling pointer to something that used to be below but no longer exists. I mean, because that was deleted before too, right? So the net effect of your removing a thing, right? You're going to be just moving this up. So that means like at any point, you're going to have some kind of queue, and it's actually going to keep pointing to old things down below. You can't change this pointer. This pointer is there forever. Okay, so that's fine. But also, an obvious weakness is that you're spending linear time to remove something, scanning the thing, right? Okay. I want to get constant time for push and remove. A doubly linked list? You want to do something like this? So, okay, so then you still want to move something up like this? Okay, this could kind of work. Okay. Okay, this could kind of work. I'll suggest one thing though. is slightly undesirable. Oh wait, yeah, okay, so this would make sense for deletion. Well, it's slightly undesirable that we still have pointers to here because garbage collection will never collect it. But how do I insert to the top? How would I make a new item? Right? So if I have a new item, I would want to put it up here, right? And I can make a pointer to here, right? And I can move this head pointer up above, but you're not able to make that pointer. Sorry? Uh, this thing is done, is a done deal. Okay. All right, any other ideas? Yeah. All right, what if we had two stacks? So I'm kind of pushing into here, right? And then I'm popping out of here. So this sort of represents the top half of the stack. This represents the bottom half in reverse order. And so now this is the bottom of the queue, can be removed from the top, right? So at least when both sides are filled up, I have constant time operations. That's good, right? But what's the obvious issue? When it's full? Well, each cell just has one pointer and one data, so it's not that wasteful. So what happens if I pop, I empty this whole side of the queue, and I try to empty another one, which means I need to start looking on the inside, but the inside doesn't facilitate removing things, right? So, right, so we're in this situation, okay? So what should you do? Yeah. Ah, we are going to, we're going to just flip it and reverse it. So we'll take this whole thing down, right? And then I'll take F and I'll put it at the bottom of the out and I'll just reverse the whole thing. I'll just flip it over. So I'll copy everything over. Okay, and then I'm ready to go for removing the next one. Okay, good. So now the question is, how do I justify? Okay, so that's the whole algorithm, right? We're making a queue with two stacks. When one gets empty, I just flip the other stack over, right? I mean, it's really like you have a big stack of plates. You're trying to take a plate down from the bottom. So you just flip it over. Now your bottom's on top. So how do I argue that this takes constant amortized time? Yeah. Okay, so maybe this could be like a credit scheme. So I understand the intuition, but to formalize it a little bit, we can, every time I insert something, I'll also put, $1 on it. Let me draw it up here. So we pay for a credit. We put a credit on everything that gets inserted. Okay. And then later, when I need to reverse it, when I flip all these over, the time spent for flipping over F is just paid for by F's credit. Okay, so I just put credits on all the items as I insert them, not the algorithm, just in your head, imaginary, and that will pay for the big bulk operation. Make sense? Anyone else have any other analysis? Yeah, so another option is make a potential function which is just the number of vertices in, which will always also equal the number of credits you have. But that's another option. If your potential function is just counting the number of plates and not inside on the in stack, that'll go from like k to 0 when you spend k time to flip them over. Okay. So I think one of the homework problems, well, maybe if not, it was just there. A nice one is how do you do a double-ended queue? Maybe to think about, right? So inserting, deleting from both sides. You can still try to do, a two-stack approach, but it's going to be a little bit more nuanced. Okay, so that's it for amortized analysis. And next time we'll start discussing some basic randomized algorithms.